In the first part of this lesson, we introduced negative binomial distribution, and we said a negative binomial random variable counts the number of independent and identical Bernoulli trials needed for the first R successes. R is an integer here. Maybe the number of trials you need to find 2 successes or 3 successes and so on. And we also outlined that the PMF of a negative binomial random variable is given by that. X minus 1 choose R minus 1 times p to the power of R times 1 minus p to the power of x minus R. And x ranges from R to infinity. We also showed that the PMF of a negative binomial distribution actually sums to 1. And we did that right here. Okay, the PMF sums to 1. Okay, I'm going to write the PMF again for a random variable x, which follows a negative binomial distribution with number of successes equals to R and probability of success equal to P. The PMF Px of little x is equal to x minus 1 choose R minus 1 times p to the power of R times 1 minus p to the power of x minus R for x ranging from R to infinity. The next thing I want to do is find the MGF of this random variable. The MGF, mx of t, by definition, is the expectation of e to the power of t times x, which is equal to the sum, right, x ranging from R to infinity, because the support ranges from R to infinity, of e to the power of t x times the PMF, which is x minus 1 choose R minus 1 times p to the power of R times 1 minus p to the power of x minus R. Okay, so you can see here, let me use a different color. P to the power of R does not depend on x, which is the index of summation. So I can take it outside of the summation. So let me just erase that, and then I have p times p to the power of R outside of the summation. Also, e to the power of t times x can be written as e to the power of t to the power of x. I can also add or subtract R and then add R. So I haven't changed the power. I've just added a 0 to the power. So I can rewrite this as p to the power of R times the summation x ranging from R to infinity of e to the power of t to the power of x minus R plus R times x minus 1 choose R minus 1 multiplied by 1 minus p to the power of x minus R. This is equal to p to the power of R times the summation x equals R to infinity of, now I can write this as e to the t to the power of x minus R times e to the t to the power of R multiplied by x minus 1 choose R minus 1 times 1 minus p to the power of x minus R. Now you can see e to the power of t to the power of R does not depend on the index of summation, which is x. So I can take it outside of the summation. Alright, take it outside, so I have e to the t to the power of R. And also, the power here, x minus R, is the same as that power. So I can combine that expression with that one. And I would get p to the power of R times e to the power of t to the power of R multiplied by the summation x ranging from R to infinity of x minus 1 choose R minus 1 which is right there, multiplied by 1 minus p times e to the power of t to the power of x minus r. Now, I'm going to let p, actually 1 minus p star, be equal to 1 minus p times e to the power of t. And I'm going to assume that 1 minus p times e to the power of t is less than 1. Of course, this is always greater than 0, so it's actually between 0 and 1. In that case, I can assume p star, or 1 minus p star, to be some sort of probability. Okay? And then I can rewrite that summation, actually the whole expression, as p to the r e to the t to the r times the summation x equals r to infinity of x minus 1, choose r minus 1, multiplied by 1 minus p star to the power of x minus r. Now, if I could multiply this expression by p star to the power of r and divide by p star to the power of r, and observe that p star to the power of r, the denominator here, does not depend on x, what I have is p to the r times e to the t to the power of r divided by p star to the power of r multiplied by, the whole thing multiplied by, the summation x equals r to infinity of x minus 1, choose r minus 1, multiplied by p star to the power of r, 1 minus p star to the power of x minus r. Now, if you look at this, that is the PMF, or the probability mass function, of a random variable, actually a negative binomial random variable, with probability of success equal to p star, and the number of successes, r, equal to r. And as we have seen in the previous lesson, the PMF of a negative binomial distribution sums to 1, meaning that the whole expression is equal to 1, because it's the sum of the PMF of a negative binomial random variable. Now, what I can conclude is that the MGF is equal to p to the power of r times e to the power of t to the power of r divided by p star to the power of r. Now, everything here has the power of r, so I can rewrite this as p times e to the t divided by p star to the power of r. But what is p star? We know that 1 minus p star is equal to 1 minus p times e to the t. It's right here. Okay? Now, p star is thus equal to 1 minus p times e to the power of t. Plugging that back in here, I get the MGF of a negative binomial random variable, which is p times e to the t divided by 1 minus p times e to the t, the whole thing to the power of r. Now we have the MGF of a negative binomial random variable x to be p times e to the t divided by 1 minus p times e to the t. Okay, that's good. I'm sorry, I forgot to the power of r here. The whole thing to the power of r. That is the MGF of a negative binomial random variable. There is similarity between a negative binomial random variable MGF and a geometric random variable MGF. I'm going to remind you of a geometric random variable y Let's say y is the number of trials needed for the first success, or the number of trials needed for the first success follows a geometric random variable, and the MGF of y, so let me say y is geometric with probability of success p, then the MGF of y is equal to p times e to the t divided by 1 minus p times e to the t. That is very similar to the MGF of a negative binomial random variable, negative binomial Rp, where x is now the number of trials needed to observe the first R successes of Bernoulli trials, each independent with probability of success p, which we have found to be right here. So mx of t is actually my of t, which is right here, to the power of r. So that's a very convenient way of remembering the MGF of a negative binomial random variable. It's just the MGF of a geometric random variable to the power of r. In fact, if you remember, the expected value of a geometric random variable was 1 over p. And you will find out shortly that the expected value of a negative binomial random variable is actually r divided by p. So r times the expectation of a geometric random variable. In fact, let's just go ahead and do that. It's very easy to show. So the expected value of x, if x follows a negative binomial distribution, is equal to the derivative of the MGF of a negative binomial random variable evaluated at t equals 0. Simply find the derivative with respect to t and plug in 0 for t. Now that is equal to the derivative with respect to t of the MGF, but I can write that MGF as my of t to the power of r, where y is the geometric random variable. Okay, because what's inside here is simply the MGF of this geometric random variable evaluated at t equals 0. Take this derivative, that's going to be equal to r multiplied by my of t to the power of r minus 1, the power rule. And by the chain rule, again, I take the derivative of the inside function, which is my of t, d by dt of my of t, and evaluate that at t equals 0. Now, this is equal to, r multiplied by my of 0 to the power of r minus 1 multiplied by the derivative of this geometric random variable MGF evaluated at t equals 0. Okay, we're almost there. We know what this is. That is the expected value of this random variable y, because the derivative with respect to t of the MGF of y evaluated at t gives you the expected value. So that's 1 over p. But what is this? my of 0. My of 0 is the expected value of e to the t to the power of 0. But e to the t to the power of 0 is 1. So the expected value of 1 is 1. Okay, so my of 0 is 1. So this gives me r, let me use black. So this is equal to r times 1 to the power of r minus 1. Therefore, this is equal to r times 1 minus p, which is r over p, r divided by p. Therefore, the expected value of a negative binomial random variable is equal to r divided by p. Straightforward. Very easy to get to once you know the relationship between the geometric distribution and the negative binomial distribution. Geometric distribution is the number of trials needed for the first success. Negative binomial distribution is the number of trials needed for the first R successes. So when R equals 1, a negative binomial distribution is simply a geometric distribution. Okay, now the last thing I'm going to do is find the variance of this negative binomial random variable x. Okay, to remind you again of the geometric distribution variance, so if y follows a geometric distribution with probability of success p, the expected value of y is equal to 1 over p, and the variance of y was equal to 1 minus p divided by p squared. What I'm going to show now is actually the variance of a negative binomial distribution is r multiplied by the variance of a geometric distribution. Let's show that. Okay, so what's the variance of a random variable? The variance of a random variable x is equal to the second moment, which is the expected value of x squared, minus the first moment squared. So that's minus the first moment, which is expected value of x, whole squared. We know the first moment. So this is the second moment, expected value of x squared, minus r over p quantity squared. So if I can find that second moment, then I am done. I know the variance. And that's exactly what I'm going to do. I'm going to find out the second moment. The second moment is the second derivative of the MGF, mx of t, evaluated at t equals 0. And that is equal to the second derivative of the MGF, which is my of t to the power of r, evaluated at t equals 0. Okay, now this is equal to the derivative with respect to t of the derivative of my of t to the power of r, evaluated at t equals 0. This is equal to the derivative with respect to t of, so the inside derivative here is r multiplied by my of t to the power of r minus 1 times the derivative of the inside function, which is my of t. Okay, this evaluated at t equals 0. Now I have to take the derivative of these two functions. So this is the first function, that's the second function. In fact, I'm going to write the first function in blue and the second function in black so you can see. So when I have the product of two functions of t and I have to take the derivative, I simply use the product rule. And that's going to be equal to the derivative of the inside, the derivative of the first function, which is d by dt of r times my of t to the power of r minus 1, multiplied by the second function, which is d by dt of my of t, plus the first function, which is r times my of t to the power of r minus 1, times the derivative of the second function. So the derivative of the derivative here is going to be the second derivative, d squared by dt squared of my of t. Now the whole expression evaluated at t equals 0. Now this is equal to, let's take this derivative. That's going to be r multiplied by r minus 1 times my of t to the power of r minus 2, multiplied by the derivative of this inside my of t, so that is times d by dt of my of t. d by dt of my of t, which I just dropped down from here, plus r multiplied by my of t to the power of r minus 1 times the second derivative with respect to t of my of t, the whole expression now evaluated at t equals 0. And that gives us, let's go ahead and substitute 0 for t. So that gives me r times r minus 1 multiplied by my of 0. Any moment generating function evaluated at 0 is going to give you a value equal to 1. So that's going to be 1 to the power of r minus 2, which is still going to be equal to 1. If I evaluate this derivative of mgf of y at t equals 0, that gives me the expectation of y. But y is a geometric random variable, and its expectation is equal to 1 over p. The same thing here. Evaluate this at t equals 0, you get the expectation of y, which is 1 over p, plus r multiplied by, plug in 0 for my of t, you get 1. 1 to the power of r minus 1 is equal to 1. Alright, and the second derivative of the mgf of y evaluated at 0 gives you the second moment of y, expected value of y squared. Okay, I'm not going to use blue and black anymore, so this gives me r times r minus 1 times 1 over p squared plus r times the expected value of y squared. But what is the expected value of y squared? Expected value of y squared is the variance of y plus the expected value of y squared. How did I get that? We know that the variance of y is equal to the second moment of y minus the first moment quantity squared. So if you make expected value of y squared the subject of the equation, then you get that to be the variance of y plus the first moment of y, the whole squared. And that's what I have. And we know the variance of y. Y is a geometric random variable, and we know its variance, and we know its expectation. So this whole expression is going to be equal to r times r minus 1 divided by p squared plus r times the variance of y is 1 minus p divided by p squared. And the expected value of y is 1 over p, so this is 1 over p squared. Now this is the expected value of x squared. But what we need is the variance. In fact, we have shown this here that the variance is going to be the second moment minus r squared p squared. We now have the first moment, so we plug it in here and find our variance. So the variance of x is the second moment of x minus p squared, minus r squared over p squared. And we have the second moment of x here. So let's rewrite this second moment of x as, let me write it down first, r times r minus 1 divided by p squared plus r multiplied by 1 minus p divided by p squared plus 1 over p squared minus r squared divided by p squared. Okay, let's multiply this term out. What I mean is, let's multiply r by r, we get r squared over p squared, minus r times negative 1, r over p squared, plus r multiplied by the first term gives you r times 1 minus p divided by p squared. R multiplied by the second term gives you r divided by p squared. Then we have this minus r squared divided by p squared. Okay, so we have terms canceling out. We have positive r squared p squared canceling out with negative r squared p squared. And also we have minus r divided by p squared canceling out with plus r divided by p squared. So we are left with r multiplied by 1 minus p divided by p squared. And that is the variance of a negative binomial random variable x.